Joe for Thursday, January 12th, 2023. Today we'll be working on LeetCode problem 1519, number of nodes in the subtree with the same label. This is a medium problem. And the problem statement says, you're given a tree, i.e. connected undirected graph, that has no cycles, consisting of n nodes numbering from 0 to n-1 and exactly n-1 edges. The root of the tree is node 0. And each node in the tree has a label, which is a lowercase character given in the string labels. The node with the number I has the labels at I. Okay. The edges in the edges array is given in the form of edges at I is AB, which means that there's an edge between nodes A and B. Return the array of size n, where answers at I is the number of nodes in the subtree of the ith node which have the same label as node I. We will set 25 minutes on our Pomodoro timer here and get started. So the first thing we'll do is convert these edges into something more useful. So the list of edges doesn't really help us if we want to do the tree traversal. So instead we will create a dictionary called nodes, and we'll make a default dictionary. Of a set. So this is going to be a mapping where the key is a node and the value will be a set of all the nodes that you can reach from that node. So it's a node mapped to all the connected nodes. So we'll say for each A and B in our edges, our nodes at A, we can add B, and our nodes at B, we will add A. All right, now we have something more like a tree structure where each node has a list of all the connected nodes. The next thing we'll want is a result, and that result is going to start out as an index, or sorry, it will be an array of zeros. And we basically need n zeros. So we have our basic result, and we will return our result at the end. Okay. And now we need to traverse our tree. How do we traverse the tree? Let's go recursively. So we'll create a new function that will do a recursive traversal. So we'll call that count subtrees recurse. And we'll take the current node that you're in, and then we will go through all of the nodes that you're connected to. So how do we traverse to the other nodes? Well, for each connected node in our nodes node. So basically we look up all the connected nodes in our handy dandy dictionary here. And for each of those nodes, we'll just recurse down that tree, down those nodes. All right, now this does present some problems that we haven't quite addressed yet. Number one, top of the list, is we are not taking into account that our list of nodes includes our parent node. So for example, 2 will give us a list of nodes that it's connected to, which includes node 0, and we don't want to recurse back up the tree. So how do we handle that? Well, we just say, if the connected node is equal to the parent, well then let's not recurse, and we'll just continue through our loop. All right, you might be thinking, well, we don't have the parent. And you'd be totally right, because we haven't passed it in, but we can. So let's just pass it in. That means when we call this recursively, we will need to call the node and pass in ourself as the parent. All right. And finally, down at the bottom here, we do need to call this at least one time, and we will start it out with node 0. And it doesn't have a parent node, so we'll just pass in -1. Okay, so that gives us our basic recursive algorithm. We're going to go through every connected node in our current node, and if it's not the parent, then we'll recurse down that path. Okay, so now we have a recursion, we have a result, but we don't really have the basic functionality yet. Well, let's just check to see if this works first. So this result will be not accurate, but we will see if we're going through every single node, and we'll see if we have any infinite loops. Okay, and it looks like we are going through every node and there's no infinite loop, so we have a nice recursive algorithm here. That's what we want. All right, so now how do we keep track of our labels? Well, first thing we'll do is let's get the label for this node. And that's just going to be labels at node. All right, good, good, that's fair. Now we need to keep a count of all the labels. All right, so let's have a label count. And we'll make that a default dictionary as well. So we're going to have a mapping from, let's see, this will be an int. So we're going to map our label, so the string or the character of our label, to the count of how many times we've seen that label so far. All right, so in here we'll say our label count at our label plus equals 1, because now we've seen this label one time at least. Okay, so that accounts for this node, and then when we call recurse, that will count for all the other nodes. Great. So once we've done all those recurses, then we can increment, or we can count our result for this node. And that's just going to be equal to the label count for this label. Okay, now that's not quite right. It's close, but it's not quite right. So one thing that we're not counting here is in this count, this is sort of a, we'll call it a global variable that's getting incremented inside of this count subtree's recurse. So this is shared within all the different recursive calls to this subtree recurse. Now when we do that, it means that this count not only includes all of the subtrees that we just counted, it's also going to include all of the labels from trees or nodes higher up in the tree, which we don't want to count as part of our result. How do we get around that? Well, in here, we'll say, well, what was our parents' count? So this is basically saying, what was the count before we added ourself and all of our subtree? Well, that's just going to be the label count at this point, before we add ourself and our subtree. Okay, so we grab our parent count, then we add our own count to this label, and then we add all our subtree counts to this label. So when we take the total count, we need to subtract the parent count from the total count to isolate just the nodes that were below this node. Okay, that should be it. Let's try that out. And that passes. Great. So we have an algorithm, seems to work. We've got a way to untangle all the edges into a tree-like structure. We have a default array of values for our initial result. We have our global counts that we're keeping track of all the label counts. We have our recursive calls that take us through the entire tree. And we have our final result. Let's submit that and see how well we do. Hey, not bad. All right. So this beats 98% of all the other solutions in terms of its runtime, which is actually blows me away. I was not expecting that. And it beats 70% in terms of memory. So that's not bad at all. There's one thing that I do want to try just to see if it'll make any difference at all. So instead of using a set, let's just make this a list. So this might take up, well, we'll actually find out. So instead of add, you have to do append. This is basically the same. It's a little bit more dangerous if they give us edges that are duplicates, so it might not be as accurate depending on the constraints. Let's just see if we can do any better. Still 98% with runtime, and even better with our memory. We beat 93% in terms of memory this time. So this shows, I think, that a list takes up less memory than a set. But I'll have to check the constraints to make sure that there aren't any duplicates. And it doesn't look like they tell us here there are. I'm guessing because the edge length is n-1, there can't be duplicates. But it is something to be aware of, that if that wasn't one of the constraints, we might have an issue with duplicates in our list of edges here. Okay, well, I'm pretty happy with that. We did pretty well. We have an algorithm that works. It's not super complicated. It's not super long. I did not describe this very well, but I hope you took something away from this. I hope this helped. All right, I'm out of time. Hope you learned something. Hope you had fun. Now go out and write some better code.